So my name's Nick Jennings, and I'm the Vice Provost for Research and Enterprise here at Imperial College London, and I'd like to welcome you to tonight's Energy Futures Lab annual lecture. So the Energy Futures Lab is one of our 6 Global Challenge Institutes, and their aim and their purpose is to bring together researchers from around the college. And to be a Global Challenge Institute, you need to have a presence in all 4 faculties that we have here at the college. So the Energy Futures Lab meets that criteria. And in fact, we have over 1,000 individuals and researchers associated with the Energy Futures Lab and doing energy research here at Imperial. So it's a very important topic for us, and the Energy Futures Lab is an important part of our multidisciplinary research landscape. For this year's lecture, I'm delighted to introduce Dr. Vera Silva, over here, who's the Chief Technology Officer for GE Renewable Energy's Grid Solutions. Vera is an alumna of the college, having received her PhD here in 2009 in the Department of Electrical and Electronic Engineering. Since then, she's had it says a long and illustrious career. I'm not sure it's overly long at this point. It's certainly illustrious, but I'm not sure I would agree with long at this point. Working both industry and academia with GE Grid Solutions, EDF, the University of Manchester, and Polytechnic Institute of Porto. She's a respected industry leader who's written a number of books and published over 40 scientific papers, as well as contributions to a range of industry-related works. This year, she was named as an everyday superhero. That's quite impressive to be named as an everyday superhero. There is a colon associated with this for women in STEM careers. So I guess you need to broaden out of that to be able and be that superhero. So we look forward to seeing evidence of that in the talk. Tonight, she's going to talk. Use her vast knowledge and experience to discuss the challenges and needs of the grid of the future, and talk about new grid solutions that are needed to allow renewables to become a bigger part of our energy system. So can you join me in welcoming Dr. Silva to the lecture?
Good evening, ladies and gentlemen. Thank you for the kind introduction. And I am really delighted to be here today, to be giving this lecture, being an alumni of this institution, of the Department of Electrical and Electronic Engineering, where I actually started doing the work on integration of renewable generation, which I have pursued all over the rest of my career and has given me constant passion and motivation to do the work each day, being that in industrial research roles, research leadership, and today as part of the technology solutions provider world. In these 10 years since I have left, there are 2 words that could define how I felt. The first one was busy, extremely busy. And this is what happens when you are working on the right subject at the right time, and you have the opportunity to work with teams of incredible people that support you, keep giving you the right questions, helping you to find the answers. And the second one is that I have been extremely passionate about each and every one of the jobs I have done, of the problems I have the opportunity to contribute to, and more than anything, about the fact that I was able to share results, communicate around integration of renewables with different types of actors. From policymakers, I had the opportunity to talk at both the French Parliament and the European Parliament about the problems of having low inertia. And that is something you would never dream you would have to do. Not because it was the parliament, but because we were talking about inertia in a political environment. And the people are really willing to understand what it is, the power system, and why it is so important for us to change it. And so I have been really pleased to have this opportunity of starting with GE Grid Solutions this summer as Chief Technology Officer, which has brought me a whole different responsibility in the domain and also the opportunity to be in the first line of developing products and systems that will be essential to enable the energy transition. But besides the fact that I was busy and working on things I liked, I also looked back at what happened in the 10 years since I left the UK. A lot of these things mean a lot to me because I was there when they happened and somehow took part. 2008, I remember my supervisor, Professor Goran Strbak, telling me that there was the Climate Change Act, and that was incredible because it had legally binding targets on the amount of renewables we would need to reduce by, I believe, was 2050 compared to 1990. The second thing which I found impressive was the creation of the Department of Energy and Climate Change. It was the first ministry that actually had the words energy and climate change together. It also represented a commitment at political level of climate change is important and we need to address this. And the Committee on Climate Change, which provided independent advice to this Department of Energy and Climate Change, and to which Imperial College teams had the opportunity to often contribute with technical evidence and discussion. Where, as well, another thing I found was that in this Committee on Climate Change, you had different voices, from engineers to businesses and policymakers that were looking at how can we make this happen. Then going from the willingness into what has been happening in terms of the changes of the system, I could see that there was the Energy Act in 2013 that concerned me greatly, that my institution by then, EDF and EDF Energy, because this was relevant to how you are going to incentivize the investments on the low carbon technologies, where we had the contracts for differences were introduced, which showed from willingness to putting the right economic incentives. And then I looked at what was happening on the system operator side, which is, this have allowed us to identify some technical challenges that needed to be resolved by technology. Having the right technology meant that we needed to ask for the right services from the system operation. Enhanced frequency response was one of the very first services that was put out there with material economic value behind to provide a service that would help us to operate a system with lower inertia. This also led to the development of battery storage because the requirements were so demanding in terms of how quick you need to react, and this technology was able to meet them. And more recently, it's also about reorganizing the actors, their responsibilities and their roles, and we have the creation in the 1st of April, but it's apparently not an April Fool's Day joke, the National Grid System Operator, which will help us to address the problem of operability and balancing the system in a transparent way and fully focus on having new technologies coming into the system and actually helping the system to operate. So there has been quite a lot happening since I left Imperial. And does it really do we see a material change in the system today? The first thing I looked was, what does the electricity mix look today in the UK? So when I arrived to France, I explained, they have little renewables, there is still quite a significant amount of coal. It's very much an electrical island, only 2 gigawatts of interconnection, which was really excellent when I was doing modeling because it meant that you could basically somehow neglect modeling the rest of the European continent. Today is a tougher job to do. And it's a system that has operability challenges because it's not synchronous to the large European system. And therefore, frequency was a serious discussion when I was here. Frequency seemed to be something people were a lot less worried when I came to France. And today, you look at what is the electricity generation mix over the last year. And what we can see, there is a significant percentage of gas, but a massive increase of wind and the coal technology that is disappearing from the mix, which means that there's a road ahead of us, but the changes that happened in just a decade are driving us into a generation mix with less emissions. And the second one, and that's big news, is that the UK is no longer an island. And that is something that was really interesting to know. It makes it harder to model. It creates interdependencies with the electricity systems of the Nordic countries, continental Europe, or Ireland, but huge opportunity to have a more efficient system to share resources from security of supply, that in terms of capacity, up to ancillary services close to short term. We started from 2 gigawatts of interconnection. We have 5 today, and this is likely to double in the next years. Most of these are already in operation. There's already the call for the new interconnections. And what I could see when I was looking at the balancing in France is that there is an increasing share of balancing services and reserves between the two countries. So this really means that when I look back at the history of the power systems in Europe, is that the first real international cooperation we had back in the 60s was interconnecting the countries for security of supply. If there's something that people has been working and moving is the internal electricity market in Europe, we can also see the UK as having this increasingly connection to the remaining of the European grid. And this transition is not happening only in the UK, it's also a political willingness across the European system. We had this year an agreement between the member states to have 30% of energy coming from renewables by 2030. That is in a decade, which from a technology development perspective is tomorrow. And what we look at is that the states agreed. The original proposal was 30%. They actually agreed on something more ambitious that was originally thought. And because this is all energy combined, it means that for the power system, this means more than 50% will be coming from renewables. Actually, these are still being negotiated, but we will get quite close to 60%. We have 30% today. So this is a very important change in terms of the mix because the hydro resources have been, for the most of it, exploited, which means that most of these additional renewables will come from wind and solar. And there's a recognition that in order to have supporting an ambitious scenario on renewables in the electricity grid, we need to have a coordinated investment on the infrastructure itself, between the national grids at transmission, but quite a lot of this at distribution level, as well as doubling the interconnections between countries. If you look at the 10 years network development plan of NSOE, we can see that there is a very strong push into reinforcing the interconnections between the countries. And this will also require a coordinated development of smart technologies that will help us to develop the right amount of infrastructure, because at the same time we're developing solutions that help us to use better the assets we have. So sometimes building the wires is no doubt the easier, but it's also very hard from public acceptance perspective and geographical constraints, and therefore we try to get the best of each world and have this coordination in terms of developing the system. And if we look even further out, what is happening in terms of the world energy transitions, we can see that this is not Europe is leading the way. Is leading the way in terms of ambitions, is leading the way in terms of deployment of new technologies, but this is actually a global goal. What we can see from, I used as a source the World Energy Outlook from 2018 that presented obviously different pathways, different scenarios that we could have in order to decarbonize the energy mix. And the first one we can see is that electricity is recognized as a key vector that will help us not only to decarbonize the electricity generation, but as well as other sectors like transport with electric mobility, as well as heat or cooling sectors, which are harder to decarbonize if we don't look for new different vectors, such as electricity. So what we can see is that in all scenarios, we have a very important increase into the renewables that we'll see in the system. Only the sustainable development scenario will actually lead us to meeting the Paris Agreement goals. So we are really likely to have an agreement and a push towards a high renewable scenario by 2040. Second thing was interesting to see in the World Energy Outlook was a special session dedicated to the power system, trying to understand, yes, we want to meet these targets, and yes, electricity is today one of the vectors that's promising to meet these targets, but we need to make sure that the power system can follow, and we can see that flexibility will be essential in order to accommodate these large shares of renewables. The report looked actually at what are the flexibility needs and how do they evolve as we increase the variable renewable penetration in terms of wind and solar into the system, and how much flexibility will the systems need as they go to more ambitious targets. And they separate between phase 1 up to phase 6, depending on how far the systems have gone. And what we can see is that in many cases, we have already used most of the simple solutions that we could have to absorb the first phase of needs for flexibility, and that we are now reaching levels where we need to think of whole new solutions that are coming, and explore all possibilities. So what I would say is that in many cases, the low-hanging fruits have been picked. And what we need to move ahead is to actually have a much deeper transformation of the electricity system from the grid technologies up to what we have in terms of solutions to flexibility. So to quote what colleagues said on the Energy Systems Integration Conference this week is that the road that took us here won't take us there. We need now a major transformation of the electricity grid, and I think you are, as Imperial College students in many cases, in one of the best places to engage into this transformation, to bring the solutions we are expecting, and to help solutions provider like my own institution, GE, to have the right ideas and drive the right products into the market. Of course, if any of you want to be involved in bringing the products closer into the market, you're also very welcome to join our teams, because one of the challenges we are facing at the moment is that we need the solutions. Developing the solutions will need talent. We'll need creativity. We need very brilliant minds sitting together, and we need a lot of them. So don't hesitate. And it is with great pleasure that I'm going to now, in the remaining of my talk, bring to you examples of what we are doing at the moment. Within GE Grid Solutions, I'll tell you a bit more about who we are. I'll remind you of what the grid transformation drivers and challenges are, for which we are looking at solutions, and what new technologies are we working on today. And finally, some thoughts on what the grid of the future could look like. GE Grid Solutions is is an autonomous business within the General Electric group, which is part of the General Electric renewable energy business. We have about 6 billion of revenue in 2018, teams scattered in 80 countries, 16,500 employees, and we equip today 90% of the power transmission grids of the world. But what I'm the most proud of is that we have 3,400 engineering teams, which I am leading at the moment, of which 1,200 are devoted to R&D, which is an important commitment for us. And among our experts, we have 1,000 well-recognized engineers who are very active in associations such as the IEEE and SIGRE, and they are recognized industry experts. We're part of Renewables today, and it makes perfect sense. Because if you think about it, what we're trying to do in the next decade is going to be integrating large share of renewables. Our colleagues from Renewables, they develop onshore, offshore wind, battery storage, PV inverters, and they want the grid to integrate as much as possible because that is their business. But we need clever solutions. So today, we have together the teams that are trying to create a grid that's friendly to renewables with the teams that are trying to create technologies which are grid friendly. And we have huge synergies that are building on with this new organization of the company. Why I feel that not only this is an exciting topic, but that I'm also in a very exciting place to be working on transforming the electricity grids. Transforming the electricity grids, actually creating them to start with, is the DNA of General Electric. For 127 years, the company has been doing this. From creating the need for electricity with the light bulbs, Thomas Edison, the very first electric vehicles, being able to electrify larger installations, designing the high voltage equipment that actually allows us to operate safely a grid that was becoming larger in terms of voltage, in terms of span in geography, in terms of complexity in organization. So our engineers have designed some of the most incredible circuit breakers, power transformers. Each one of them is really a masterpiece of its own. And there were engineers working very early on the HVDC technologies. From Uno Lam, developing who we call today the father of HVDC. So in fact, we have a very strong motivation within our engineering teams to continue this heritage. So as I was telling you about, to do this, we need people and we need infrastructures. So today we have 1,000 R&D teams. They are in 17 different countries, with the majority located in Europe. First country in terms of the size of the R&D teams is France. The second one is the United Kingdom. So we have not only a very strong heritage of R&D in power grids in the United Kingdom, but still very strong teams that are working in many different topics. We're also supported by research institutes or large labs. We have collaboration with a number of universities. One thesis at the moment with Imperial College, collaboration that should be strengthened in future, I hope. We have labs which are serving today the development of new technology. So Supergrid Institute, it's an interesting concept. It's an energy transition lab created by the French government, of which GE is the largest shareholder. And they're working on both HVDC, the design and the configuration of the grids of the future in terms of supergrids and mesh DC grids, as well on new technologies for high voltage equipment. We have obviously a need for high voltage labs, which are actually of a scale and complexity that only a very high voltage equipment manufacturer really requires. One of them is placed in Lyon, which is Arc Cerda, and this is also where we test new materials. And finally, we have new concepts of labs, like the Digital Energy Innovation Lab, which is actually a mobile lab that's looking at microgrids or device management interfaces so that we get the right interface between the distribution and transmission, digital tools, and what you're going to have at the edge, an aggregator, if it's a generator, a virtual power plant. And with this lab, we can test this, and we do it with the client. So just to tell you how important the UK is for us, we have today within GE 16,000 people, 1,800 working on grid solutions, and research centers in Cambridge, UK, large research center in Stafford, mainly focused on HVDC, grid automation in the Northern Ireland, and power system stability in Scotland. And what we do with all these people. So basically, what is our space of action today, from which I will derive different examples of research. We're working on substations, digital substations, distribution and transmission, as well as the substations we're going to have in the generation or the renewables, FACTS devices, HVDC, and importantly, everything that's around digital grid software. So the tools you're going to have to operate a transmission grid or a distribution grid, as well as the platforms that you have to run a market, an electricity market in a country. And we're trying to solve with our clients four big questions, big challenges they have. The first one is about connecting the generation. We have a massive explosion in new generation coming into the grid. We have also large offshore projects that need to be connected over long distances. And at the same time, distribution grids being under pressure with the arrival of decentralized resources. We're helping the clients to answer questions on integration of renewables from a technical perspective. What technology we need to help to stabilize the grid, to help you to manage a system with less synchronous inertia and lower short-circuit strength, how to do grid forming, and basically create a grid when you have fewer and fewer synchronous machines. We're helping to balance generation and demand with different solutions to flexibility, both digital software as well as hardware, such as battery storage. And finally, we have a very strong push on reducing grid environmental footprint. A low-carbon grid is not only a grid that we feed with renewables, it's also a very large infrastructure, actually the largest industrial system that was created by mankind, which has to be built, will have an impact on the system where we place it, has equipment that use materials that have greenhouse emissions that can be toxic. And so there is quite a lot of work on having to reducing the impact of the grid assets themselves. And now I will talk to you about some examples, because it would be difficult to tell you about everything. So I picked some examples of R&D work that's being done by the team. To do this, I'll remind you of what are the trends which are disrupting the sector today, for which we're developing our different technologies. We have, of course, decarbonation. I have talked to you a lot about that, but for us, the problems we try to address is how to handle a generation that's becoming more variable and difficult to forecast, how to maintain grid stability and flexibility. We have a push in decentralization. For example, in Europe, in many countries, 90% of renewable generation is connected to distribution grid. In future, there will be periods where all the generation in a system is going to be fed from the distribution grid. This is a complete change from the classic one-way flow from large generation plant through transmission to distribution up to the end user. Now it can go both ways. It can come from any layer of the system, and the purpose is integrated so that we don't have to curtail and to waste the low-carbon electricity. In terms of concrete problems for us, is how can we, through digital tools, enable an active, the consumer to become an active actor of the power system. There's quite a large potential of flexibility in the demand side, namely from industrial loads, which can be used to support the system operation, but you need to be able to have the right tools and processes to unlock this potential, maintaining the security of the system. The complexity of the distribution grids is increasing. And at the same time, we realize that we don't even know exactly what is in the low voltage grid. So the first work was not to say that the distribution grid is going to become smart, is to be able to observe what it is, what the assets are, to monitor them, and then take actions into control them, into making them more active. And the last thing is about the exponential growth of devices in the grid edge. The distribution system operators, transmission system operators, they need to operate their system, and they need to understand what's connected to the system, because that's how they keep the system working. What we can see is that you go from 100 generation installations connecting to the grid. Today, in the UK, you have 13 gigawatts of PV, which is quite unbelievable. Having lived in Manchester, I would never, ever expect this. But these do represent 1 million generation installations that are connected to the grid. And this is an issue that's been faced by our clients all around the world. And we have electrification. This brings us back to where I started, where I mentioned that electricity is a vector that we can use to decarbonize other energy usages. But you need to connect these loads. You need to absorb them and to manage their increase. So at the same time, we're helping our customers to manage a growth in electricity demand, to be able to use energy system integration approaches where we can go and look at flexibility across different systems and use them as new flexibility sources. What we can see is that today, often the clients say that they are somehow stuck between a generation that's becoming more variable and harder to predict, a demand that will increase and is going to change its nature, while they're managing an aging grid. And they will still need to keep the lights on. And so this is why this is a challenge, and they are looking for new solutions. And one of the opportunities we see is through digitalization. It can help us to manage the growing number of connected devices. We are deploying smart sensors, PMUs, basically phasor measurement units that allow us to know more the status of the system. We have more data that's coming, actually more than we can handle. And we have new software capability. The speed in which you could solve an algorithm in the past and what you can solve today within minutes is completely different, which means that maybe you can use that to take decisions much closer to real time. So this is an opportunity, but at the same time, this connectivity that we're increasing can also bring new vulnerabilities to the system. And this is why, as we bring in these new devices, these new technologies, we need to make sure that we have reliable cybersecurity and that we are not adding a new vulnerability to the system. The digitalization will help us to orchestrate generation. The grid itself has a lot of flexibility that we can deploy if we can operate it more smartly by using the right grid software. Data management and analytics has shown to be a powerful tool, not a magic bullet, but it has shown that we can often, through very simple solutions, improve our tools, as well as giving decision support information into the grid operators, both at transmission and distribution. And machine learning and artificial intelligence has already given us a lot of benefits in its applications to forecasting, being that forecasting demand, renewables, or inertia, which I'll take you through the example, as well as support tools for services, grid maintenance. We're moving from what you call the time-based maintenance to asset condition, or what you would say predictive maintenance. This is greatly facilitated by data analytics. I won't go in detail, but what we can see is that today we have fundamentally a frequency and flexibility issue being solved at transmission. At distribution, we started fundamentally with the voltage and the protection issue as we increase the connection of renewables. In terms of flexibility, it is being a challenge. The example there is really has been worn and used, but it's a very good example with the California duck curve, which is no longer only a problem in California, but everywhere. We can see that we're managing ramps which are becoming more important, not because they are not only fast, but they will last long and over several hours. We have to ask more from renewables. We need to have what we call grid-friendly renewables. We're asking them more on fault right-through. They have shown an ability to have volt-var regulation, basically voltage management. We are asking them to provide flexibility with curtailment and to contribute to frequency regulation. All this has been proven as something that works and the contribution renewables bring to the system. The second thing is supporting system operation. DERMS, distributed energy resource management tools, have gone from something that we were hoping the market would come to something that's becoming mainstream for both transmission and distribution. You need tools that help you to forecast the resources, to manage the grids on the with different levels of renewables, and to act on both the grid components and the flexibility at the edge. DSO-TSO coordination. As I mentioned before, if we have large amounts of renewables and flexibility connected to the distribution grid, we're still doing the system operation and the balancing at transmission level. These two actors and systems need to talk to each other, need to coordinate, and they need to have the right tools. And when I talk about tools, it's actually many things. It goes from having interoperability between their tools, the ability to exchange data and information, and to coordinate decisions. And we need new tools to help us to operate the system with lower inertia so that we don't systematically curtail renewables, so that we can keep more synchronous machine in the system, because that's how we are used to do it. But you need to have the right tools that give the trust to system operators to operate the system differently. And we need to deploy the potential of flexibility from distributed resources. This is something that we talk about, that is starting, but we need to go faster, and we need to foster the distribution energy resources participation to system services. We need new concepts from virtual power plants, aggregation, microgrids that will be supporting the operation of the system. The challenge of inertia, it's something I think is very dear to the UK power system, as it was very dear to the Irish power system over several years, is that as we have less and less synchronous machines in the system, we're losing a property that actually helped it to tie together and react in a purely physical and natural way, almost instantaneously, once you had an event. That helped to stabilize the system, for example, if you lost a large generation plant. It was something that smaller systems started observing very quickly as you connected more and more devices which are interfaced by power electronics, such as wind or photovoltaics. They say we have less inertia. We don't know if our system will be able to maintain the stability. And it started as being seen as a problem for small systems. But recent studies I use an example of a study by EDF, R&D, but more recent studies from ENSOE confirm the same trend, which is that even in a large continental system, as you increase the penetration of renewables, you're going to have periods where at a given moment in time, the majority of the generation is being fed by devices which are interfaced by power electronics. And therefore, they won't naturally help the system to stabilize after an event. And what we could see is that for 25% of the time, you would have a risk of violating security limits in Europe with 60% renewables. That would mean in 10 years, if we look back at the scenarios I showed before. So in order to avoid RES curtailment during these critical periods, we need new technologies and we need new tools that help us to stabilize the system, just like what I mentioned before with enhanced frequency response in the UK. And finally, unlocking flexibility from distributed energy resources, it seems a natural and obvious option, and you wonder why isn't this happening at the moment. It's actually a complex thing to implement when you're looking at the scale of a distribution grid, and especially the point where you're starting, which is a grid that has little observability, and when you go to the lower levels of the grid, you have very limited controllability of the grid. So we're starting from a stepwise approach, which is developing the right tools, making sure that the consumers will have, the devices connected to the grid will have the ability to receive the information, and they can act in terms of, for example, curtailment or redispatching their generation or changing the settings for voltage regulation so that we can start, in fact, unlocking this flexibility step by step. This is an example of a piece of work that was coordinated by Imperial College, which I really wanted to recommend because it is a report from the EUC's Flex European project that also represents a great example of cooperation within European countries to understand what are the challenges we need to address to have these more than 50% renewables in 2030. What does it mean in terms of technical challenges? What are the issues that that will drive this? I mentioned inertia, I mentioned short-circuit strength, the ability to start a system or managing the uncertainty, and what are the solutions we'll need to work on. And as we can see, there isn't one solution that fits all. We need to have new equipment and systems. We need to have new digital tools. And we also need to have the right organization structures, from market design to recognize the value of the services, to TSO-DSO cooperation, cross-border cooperation between TSOs, and the right grid codes. And all these will result from a joint work that involves all actors, from the generation to the grid operators to the technology providers. So I really recommend this report for those who want to know more. And I'll talk to you now, just take you through some examples of the new technologies that now personally GE is working on to transform the electricity grids. One of our domains of activity in which we genuinely believe and keep strongly investment are HVDC and FACTS. These two technologies, namely HVDC, as challenging as they are, have a crucial role to play in a system with large renewable penetration. We need to connect the offshore wind farms. As we get longer distances from the shore, the connections are done through HVDC. We need to interconnect the countries so that we can benefit by the smoothing effect we have for managing variability, as well as the sharing of resources across the border. HVDC has a key role to play. And FACTS devices will help us to stabilize the grid and squeeze more capacity from existing grid. It helps you to control the flows. It helps you to use our grid differently and to operate it closely to what we would call the network stability limits. So both technologies have a key role to play. This is done in the UK. HVDC and FACTS is in Stafford. Neil is there, he's the leader of the site. And we have new buildings, new HVDC simulation lab, new valve test facility. It is the most effective technology for long distance, for transmission and interconnection of grids. And today, GE has success in some large new projects, from Rio Madeira, the longest HVDC connection we know, to the recent France-Italy link, and DolWin 3. The last two are voltage source converter technology. And what we have learned along the way, knowing that it hasn't been an easy road, because developing new technology and implementing voltage source converter has come with some technical challenges, it has been also a success for us to see that the last project, DolWin 3, which our CEO says when he visited it, that is something more complex than he believed anyone could build. Once he actually landed in the platform on an helicopter and seen what HVDC looked like, not only those results that were not always what we wanted at the leadership meeting table, he was actually absolutely passionate about the success of the project, the success of the implementation, and the technology step that we have given. And there's always the room for improvement. So what we're working on is how to reduce the footprint, increase the reliability of the voltage source converter, and provide new digital tools that are going to help us with the monitoring and the maintenance program of the different projects. So Illumina was our last project launch and continues to be a platform of innovation for us. And one of the biggest achievements we had there was to be able to basically reduce by 50% the footprint of the control system. We had increased the redundancy, which increases a lot the reliability of the system without a massive increase on the complexity of the architecture itself. We have been able to implement IEC 61850 data exchanges to improve the interoperability. The system is modular, secure, and much simpler than the system we had before, complying with cybersecurity demands. And this is something I have learned in the product industry, which is not enough to have a good idea. It has to be something you can manufacture with the less mistakes possible, and something you can implement in an efficient and simple way, because these things will be built and developed in the most remote places or in the middle of the sea. So there's more than just to have on innovation than just having a new idea. It's designing the whole system. And at the same time, we try to improve the type of digital technologies that the clients would have when the project is in operation. So one of the things was about having the ability to connect more data on the system and providing a data analytics layer that could help you not only to monitor the device, but also to plan better the maintenance of the system. The maintenance of an HVDC system, especially on offshore, it's a complex task that requires good planning. So once you are equipping the system, you need to think of how it's going to be used in the long term and what tools we need to have to facilitate the job. And this is why the digital tools that you build around an HVDC new system are somehow a step forward in terms of how you can operate it. So if some of you know, one of the things people were saying about the voltage source converter technology is that it had low reliability. And the data was showing that. And this is why in the new systems, it's one of the focus, increase the reliability so that the technology can do the job. I won't go in many details, but I wanted to tell you that one area where continues to be an important need for innovation is on the converters themselves. These are huge equipment that have quite a lot of losses and that need to have a constant reduction on footprint and increase in efficiency. Modular multi-level converters are the technology today, but we're working on going beyond and exploring the possibilities of a series bridge converters so that we can have higher density and basically further reduce the size of the valves. I'll tell you a bit about high voltage equipment because it's often the forgotten part when we talk about the power system of the future. But it's also the heavy lifting and one of the most complex pieces of technology that you can bring into a power system. And it's something you cannot do without. You need the power transformers, the circuit breakers, you need the gas-insulated substations that you can build in the cities or place underground, and you need to continue innovating in this space. One of the challenges we have today is that we talk about a supergrid, a mesh DC grid in the Northern Sea. There's many drawings and photos about it. And one of the things I found out is to do that, you need a DC circuit breaker that has a size that can actually be produced, and more importantly, that fits in a lab that can test it. And so I realized that in order to make this happen, there was a very simple piece of material that needed to change fundamentally, the DC circuit breaker. And this is where we went back to the old GE tradition of trying to think how to approach this from a completely new technology innovation, because we can't do this with step changes. We can't do this by optimizing the system. We need something new. And this is when we looked at the Global Research Center of GE, and they were working in these plasma tubes, which sounds really old, going back to the beginning, but it's a new application. It's a new approach to what we call now the gas tube, which would fundamentally change the size of high voltage equipment and give you access to this missing link. And this is something I'm very proud of today because the prototype has been developed. It has traveled all the way to France, to the Supergrid Institute. It has been integrated in a prototype of a DC breaker, and the tests are being done. So this is some fundamental step change you need to have on a very basic component to give that leap of having your meshed high voltage DC grid. Second innovation, which has been crucial. Everyone told me if you want to do high voltage equipment in reasonable size, you need SF6. If we want to have a gas insulated substation, very compact, which you put in a city, you need SF6. It's the only dielectric gas that can actually help you to reduce the size of the equipment. A lot of people said there's no alternative yet, but the problem is that it's one of the green gases with the most impact on the atmosphere, and therefore it was a priority to develop an alternative to SF6. And this is something where the teams work hardly with materials and chemistry experts to develop a green gas for grid, G-Cube, which started by being just fundamental technology innovation and is now starting to become a full range of products and is currently an industrial product which is being deployed by transmission system operators like the French TSO, National Grid, or the Spanish TSO, REE. It's a proven technology. We keep working on it so that we can go to higher voltage levels and that we can fully exploit the potential. But what was a big win was to say we can do it. It has the same size. It reduces the environmental impact by 99%, same footprint, and it works in operation. And it doesn't stop there. You need to think of the whole eco-design of a product like this. You need to find new oils, ester gases for power transformers. They have oil, there are leaks, there's an important impact on the land around. And we're looking at recyclable thermoplastics. You have a lot of plastic components in the different equipment. So it never stops. if you want to really reduce the footprint of the grid, there's always a next question to answer. Grid automation, I won't take too long because everyone knows grid automation is the area to innovate in the future, and a lot of people are working on that. Our priority is to have the intelligent digital substation. Substations, again, reducing footprint, making communications faster, collecting more data. Digital substation reduces in terms of size and footprint by 50%, the substation. You move from analog relays into digital relays. You replace cable communication by fiber optics, and you create a software platform that not only will improve your ability to operate the substation, but that is a platform to new ways of controlling the substation and the grid in the future. One of the challenges I mentioned before was about bidirectional flows. How do you keep your protections working when you have less short-circuit strength, when your flows change and the properties of the grid change continuously? You would need to basically remotely and automatically upgrade the protection settings. And that seems easy, but it's actually a very difficult task if you don't take this step through the digital substation and the complete new platform around the software. And this is where we go. Once you have this digital substation, you can then develop a number of applications that will help you not only to operate the substation itself, as well as the grid around it. And this has unlocked an opportunity of looking at new optimization and controls of the devices connected at the edge, of the grid devices that will help you to control the flows, as well as applying new techniques on machine learning and artificial intelligence to basically change the way you have your automation of your grid and you operate your automation of the grid. And so this is, again, a new field of research that is open and active for us at the moment. Of course, there's so many things from drones to cameras that are helping us to understand what's the health of the grid. How do you do your services? And so this brings me to digital energy. And this is the last point, and possibly the one in which I worked the most during my days at the Imperial and since. It's about the software you're bringing into the grid that will help you to operate from the renewables that are connected to the grid, the conventional plants, the transmission, and the distribution. Everything that's going to enable the grid edge, everything that's going to help you to operate the grid with more renewables, and what's going to unlock data analytics and help you to create digital twins of your grid. In all the different equipments, you work on creating a digital twin of the equipment, but then you need to connect them to have a digital twin of the grid. And this is the type of work we're doing around the grid software space. What was interesting is that we started from something where you had separate contained tools. We have our distribution system operators. They want a certain set of tools. We have the transmission system operators. They work on their tools. And we have the market operators who then have the tools. And this would never talk. These teams would not necessarily work together. They focus on the client. But now, as the system changes, it actually becomes all interlinked. And so rather than having just a map, we have a round structure that goes from the grid operation to having supporting a digital workforce, to having the tools from asset management. And these need to be connected and need to be thought by having this end-to-end vision of what it would be to orchestrate the grid of the future. And so the first challenge, which is a basic one, is about the data fabric. Another thing we notice is that within the clients themselves, you're going to have data silos. You will have the data that's being used to operate the distribution, the data that's being used for the transmission, and a lot of these exchanges would need to be done manually. So one of the first things is to actually understand how are you going to design a data fabric of an IoT system of the future that will facilitate the interoperability of this data and to actually coordinate the operations of the different systems, even if they are run by different actors. The second thing was about what can we do with this data in terms of bringing up all of it to apply machine learning, artificial intelligence. Only if you have a robust data fabric, you can actually truly benefit from the benefits of having artificial intelligence of machine learning. So this was a simple thing, but it's one of the first objectives. The second one was going from there into a system that today we're going from reactive and responsive operation of the system into a predictive operation where we have a lot more analytics and decision support tools that will tell you how your system is going to likely to behave in the next hours of the future so that you can take actions into what we call a much more reactive system. So this is where we're going into prescriptive. A lot of these things could be done automatically with the support of the software. It would minimize the impact of these disruptions and disturbances and would have a lot of the processes automated. And we imagine that in the future, this will be an autonomous system where quite a long set of decisions could be done by the software, by the digital layer, without the need for the intervention of the operator. So this is the road we're going. We have to develop modular apps. We need to have a common data layer. We need to be careful. We need to have good user interface, and we need to ensure the interoperability. And I know this is getting long, so I'll go closely to one example, because I think it's good that you go from this to one example of application, which is something that was developed and implemented successfully to manage low inertia grids and somehow brought together all this knowledge I have been talking about. I will take this through two case studies. One of the things is how you understand inertia and how the vision of inertia has evolved. The second one is how could you measure this inertia by making the use of all these devices, these PMUs, which are being deployed in more and more numbers across the system. But knowing you have a problem still doesn't fix the problem. So it was great for us to understand that maybe you can measure the inertia, you can even predict it, but you needed to connect this into acting on fast frequency response services so that you can bring the system back and survive an incident. So this is what we were looking at. What characterizes the problem of inertia? Your frequency moves faster, it goes lower much faster, and it has a much steeper ramp once you start moving, once you lose a large plant, for example. But we felt that it is a system problem. So there is one inertia, one frequency at the system level. And it's often where we stop the thinking. But in fact, as you start having more renewables that are integrated in different areas of the grid, this is no longer uniform. You're going to have areas of the grid with very low inertia that will be remote from the remaining conventional plant. So if you have one number, it looks like it's going to be all right, but in fact, the system will not survive in certain areas. So what we could see is that you would have, this is what the phase measurement units which are connected to the UK grid has showed, is that you actually have a frequency behavior after an incident that is quite different in the different areas. And this was something we needed to address in terms of tools. So the first thing was understanding in a system what are the areas of inertia. How would the rate of frequency change behave in these different areas when you have an imbalance? And we could identify that in different areas you would need to have different measures, and you need to activate the fast frequency reserve not in the other side of the country, but in the area in question. And this was a change for us on how you needed to address the problem. So the first thing was to use the PMU data and create a way of calculating what would be the inertia in these different regions based on the data that was being collected. And like this, we could actually estimate what would be the rate frequency change across the different boundaries and identify where would you have the problems and where you would need to focus in case you had an event. The tool has been validated through different methods. And the second thing was to say, can we go further? Can we actually predict how this is going to evolve over the next hours? Can we have an inertia prediction in the different regions that will raise awareness to where we need to place this fast frequency response and activate them? And this is where machine learning came into play. We had huge amounts of data coming from the PMUs, and you could actually train an algorithm using machine learning techniques that would take you from the point where the system was, the programmed dispatched, programmed renewables, and help you to predict the evolution of the inertia on the different areas over a 24-hour time span. And this was actually something that we have successfully implemented in the tools, but that will give you information, but you needed to collect this with the activation of the fast frequency response. I'm talking on something that needs to respond in 0.5 seconds. So if it's not done automatically and efficiently, the system is gone before you can think. So it was a very good example to say, and now what? And so we had the opportunity through the Migrate project to test how to apply this technique and use it to coordinate the fast frequency response from different resources in the Icelandic system. We noticed that in the system they had problems of inertia in different regions. We could see that the angles were diverting after an event, and the tools we developed were able to give you the information. Inertia estimate, inertia prediction. But you needed to go further and implement the fast frequency response resources, and we needed to use new solutions for that. A combination between hydro resources, aluminum smelters, and fish factories. That's what you would have available in the Icelandic grid. Each one of them would need to have the parameters and the automatic way of reacting in an autonomous way from the system that would predict that the problem was going to happen in terms of inertia in the regions. And this was successfully trialed, and that was the first step, was to say, yes, we can operate the system with low inertia, and we can use new resources to stabilize the system. The last question for us was to say, can this be scaled up into large systems without increasing its cost and complexity? So again, taking one step into the final product. So this is an example that we're very pleased of, and that has given us a long way of understanding you can do more about operating a system with low inertia, and you can resort to new flexibility sources to stabilize the system. So with this, I would conclude with some visions on the grid of the future. What I would say is that we cannot know what the grid of the future will look like, but there are things that we have convictions that will happen. One of the things is that we will need to decarbonize, and we will need to respect the energy trilemma: decarbonizing, maintaining security of supply, and keeping energy costs low. That's an expectation from consumers that has not changed in the line of the energy transition. We will need to leverage new technologies and digital tools to balance this system on a millisecond basis, resorting to flexibilities that are across all layers of the grid. from high voltage up to behind the low voltage consumer. We will need to fully exploit the potential of data analytics, artificial intelligence and machine learning. That will help us to reduce the costs and increase the reliability of the system. And we also think that this will be the preferred domain for talented resources to be working in the next years. Everyone will want to be working for grid, on the grid of the future. So I believe that creating a sustainable energy future is not an option today. It is an urgent necessity, and it's something we can do together. Thank you very much.